So last time we looked at the hose pipe rodeo, right? The guy hanging on a fire hose with water coming out of it. So this is kind of an equivalent, a bit more practical in terms of moving around. A bit dated, I think. Tanks with that, I don't know, presume it combusts, and it's a little hot jet that comes out that gives you enough lift. And it's really not that different from what we looked at San Francisco International, a jet airplane with a blast pushing a truck off. If you imagine that rotated upwards, so the blast is downwards and impinging on the ground, it's the same process. You're destroying the momentum of the jet that comes out when it hits the ground, and that's what allows you to be elevated. So anyway, so we'll look at a few things that show us those effects. Come on in. I always think this is an interesting one. Don't want to show all of it. I know exactly where I was when I did this. It was 1990, and I was going up to Canada to give a short course on some of this, graduate short course on some of the stuff. And of course, to go to Canada, to Toronto from here, you have to essentially go across Niagara Falls. But you don't go across Niagara Falls like this. I think the guy's name was Jesse Sharp. And he decided that he would go off Niagara Falls. You see the kayak right at the top there. They found his boat somewhere down in the rapids below. I don't think they ever found his body. I think he might have been a guy from Tennessee. I don't know exactly why he was doing what he was doing, but there are lots of documented events of people going off the falls in a barrel, completely enclosed, and surviving at the bottom. So you end up in a wine barrel size, not a keg, a wine barrel sized enclosure, and then when you hit the bottom, if you can withstand that somehow, you'll survive. So the other interesting thing here is that we said that Bernoulli equation is just F equals ma, and so in many respects you can think, and you can see it here, perhaps not so clearly, but if you look at the velocity downwards at which the guy is traveling, and you look at the velocity of the water that's accompanying him, they're exactly the same velocities. And so if you drop a can of water off the top of your house and watch it fall down, the rate at which it will fall is exactly the same as if you dropped a can of beans. It's no different. It's exactly the same laws. It's just that we're talking about individual packets of water which do that. And so we'll do an example which is evocative of this particular one today. And a National Geographic page which essentially talks about riding barrels over the precipice, in case you don't believe me. And finally, more related to what we'll talk about today. So we talked about, you remember that we talked about accelerating fluids on Monday. Container, run across the front of the room, it backs up. The reason they have the train carriages that are flared. So we can talk about linear motion. We can talk also about rotational motion. And so yesterday, Wednesday, last period, we talked about linear Bernoulli equation, looking at linear acceleration, which is an unleashed packet. It's like the packet of fluid, but without the packet around it, and looking at it at 2 points. We can also talk about rotational behavior. And so this is looking at exactly that. And again, making this connection between Jesse Sharp, who's a kayaker who goes off Niagara Falls, who travels down at exactly the gravitational acceleration of the water. And here we can talk about rotational acceleration on this little gizmo, where you can loop the loop and still not end up on your roof, on the floor. And so you can guess, of course, you have to go at a certain speed, you have to get enough up enough speed. In this Jaguar, I'm not sure what the model is, but if you go fast enough, you can loop the loop. And they've got 2 different loops to do it. And so you could imagine that if you didn't get enough speed up, you could imagine what the consequence might be. And so the question would be, what if you make it a bigger radius or a smaller radius? Do you need more or less speed? And so that's part of what we'll aim to talk about today. And the corollary of that for really what we're talking about would be this. So just to get you in the mood with these things, give you some reason for what we're talking about. I don't know what this is, but anyway, so you could imagine the same thing with water in it. And so I don't know if this is a mock-up. It doesn't look like Six Flags to me, but it looks like a mock-up of something they're trying out, and you can see exactly what it is. I don't know, they try something in it, but I'm not sure. Did they ever have the NASA thing take off yet? I don't think so, right? The first NASA is with a bunch of mannequins in it, no people in it, and they still haven't done that. And I kind of guess that might be what they're doing here to test this out. Probably a good idea to put a sandbag in it or a mannequin in it first before you try it with people. But it's basically the same idea. It doesn't look like they have a lot of water going down it, just enough to lubricate it. So perhaps it's not water so much that's flowing in it that you can imagine, but it's more just the person. So it's not so different from the car in that it's a solid object going around, and the water is just providing lubrication, so there's no friction, so you can get some speed up. And of course, in reality, you know, I think we're probably, are we 90% water? We're a huge percent of water. Bones would be separate from that, but blood certainly is 90%, is mainly water and some other stuff in it. And also our muscles and fat is essentially that as well. So anyway, so that's what we'll talk about today. So that kind of sets the scene for this. So I will put that in store. I'll go back to this. And so our plan today, I thought we'd do a couple of different things. This is what we stopped off at last time, before we started talking about Bernoulli. And we missed a whole bunch of stuff that I didn't have to deal with. But before we go, so what we'll talk about today is Bernoulli in a linear system along a streamline, which we talked about last time, so we won't repeat that today. Whoops, didn't want that. We'll talk about along a streamline, which we've already dealt with, and then we'll talk about flows normal to streamlines, which are rotational flows. But before I do that, I got some interesting questions at the end of class last time, and also by email, and so I thought it might be just useful to tie up this question that we did related to forces acting on a truck, just to clear it up and to make the points I wanted to make. We kind of ran through it quickly, but the idea was that we could calculate the pressure at this point from stagnation. And so I drew the pressure distribution as this, as you'd expect. And the reason for that is it's a gas that's flowing. And so as you go down in the gas, the pressure really doesn't change very much. So it's uniform on the back. And so I calculated the force due to this as just the force is equal to the area of this times the magnitude of pressure, of course. You know, you can imagine this as being the area, of course. I don't do that. The area, of course, is the area of the truck, not the top area, but it's this back area, right? So this is the area A, and this is the pressure P, and this is from stagnation, right? The fact that it was traveling at a big velocity out here, and that velocity has gone to zero as it hits here. All the momentum is transferred into the pressure. And as a result of that, we could use the three steps that we talked about in fluid statics. Is that one, we calculate the resultant force, which is the unit weight of the fluid multiplied by the area times the depth of the centroid. So these two terms here, let me write it out, unit weight times h sub c times area. This term here is basically equal to the pressure, right? We go down a certain depth in a fluid, at unit weight gamma w, and it equals this. Here we go down that magnitude, and there is no gradient because it's merely a uniform distribution. And so we know that for this case that the centroid where it acts is at half height. This height is equal to this height. And so we have both the magnitude of the resultant force, which I used, which is P in this particular case. And we now want to know where it acts. We know, because the uniform distribution is here, that if we take the moments of this distribution around any point, we'd end up with this at half height in this. If this happened to be a liquid flowing on the back of our truck, then the distribution would perhaps be this. And in this case, we can calculate again the equivalent force that's reacting, but we know that it acts two-thirds of the height down and 1/3 up. And those are two standard results in terms of a uniform distribution and a triangular distribution, that if we want to combine them, we can find out the point of action. And in this case, it's pretty simple because we just got a triangular distribution. But if we were below the surface, so we're adding an extra pressure to it, then we'd have two distributions. We'd have the force from this square area and the force from the triangular area. And we'd have lengths for each of these from where they acted upwards, L triangle. And we could write an expression that around, say, this point, if we wanted to, that the force of the triangle multiplied by its lever arm plus the force due to the rectangular distribution times its lever arm is equal to the total force, which if we resolve it horizontally is this, right, multiplied by its lever arm. And the point is that we don't know, I want to use a different color. We don't know exactly where that lever arm is, F resultant, and this term here would be this term, say total, or resultant, I guess. And so in this, we know this, we know this. We know L triangle is 2/3 of the way down, 1/3 of the way up. We know L square is halfway down. We know both of these, and the only unknown is the lever arm. So if we want to know where it acts, we can take a moment around any point that we want. It could be this point here, if this is the truck that we have. If this is the truck that's being impinged on by liquid water, and there's a pressure that's acting down on it, such as this, then this would give us the location of the resultant. And we could, if we wanted to, take moments about this point here. We could take them about anywhere, so long as we were just doing the second part, which is finding out the location of that resultant, where it acts, absolutely where it acts. The third part that we talked about in statics was that if we want this truck to roll over, we have to take moments around a specific point. It fails in a specific way. It gets blown over, it rotates around the wheel on the downwind side, away from the jet, and so a reasonable failure mode would be to do this. And so what we did is we took the weight, which acts through the centroid, which is just the center of gravity of this, which is half the way along the truck, and we equated it, the weight times this length, had to be equal to the, so we just said the FR multiplied by LR equals W LW. And again, we know where this is, we know this dimension, we know the height at which this acts. For a uniform distribution, it's half height. For a triangular distribution, it's a third height. For a combination of triangular and horizontal distributions, it's somewhere between those. And of course, we can get that from this other expression you'll remember, which I won't go into. Is it YC over, I can't remember, something here. And so in this particular case, the only thing we don't know is we knew the force. We were calculating what weight of truck does it take that it doesn't blow over. And it was 15,000 newtons, which is 1,500 kilograms. And that was our solution. And so that was our end game, I guess, for dealing with that. So just to make the point that that's the case. Another question that came in on email was, what happens if we do the calculation in absolute pressure or in gauge pressure? These are all in gauge pressures, right? We're taking atmospheric pressure as 0, and so atmospheric pressure is acting on this side, and we're taking it equal to 0, so we don't have to have a force that's acting. If we were to do our calculation in absolute pressure instead of gauge pressure, what we do is we'd add 100 kPa onto this distribution here. And we'd add 100 kPa onto this distribution here. And the answer would be exactly the same because they cancel out on both sides. And so there is no difference if we use absolute or gauge pressure. Typically, it's easier to use gauge pressure because the pressures acting on the outsides of structures are going to be 0. So atmospheric pressure as a gauge pressure is 0, but as an absolute pressure, it's equal to 101 kilopascals. Okay. So I mentioned that. So no mystery here. The question 2 on your test is a question that probably involves something like that. So 3 steps. Magnitude of the resultant and how to calculate it, location of where that resultant acts and how to get it, and then what to do with it to see how something fails. It's no great secret in terms of what that might be. All right? And everyone gets to know this, even the people who look at the videos after the fact. All right, so back to what we'll talk about today. So to recap, we talked about Bernoulli in these 2 modes. They're exactly the same equation. If they come from the same expression that I had as if I'm accelerating across the front of the room with fluid in a container. This is in its kind of raw form, if you like. This is if we integrate it. If we integrate an expression, instead of being 0, then we get a constant. Physically, what it represents in terms of our geometry, looks kind of like a whale. I don't want it to be a whale. In terms of the geometry that we're working with. And this was the idea that we had a normal and a streamline direction. We'd have multiple streamlines. We did this last time. I think we called this point number 1. We called this point number 2. I don't think, or perhaps we call this point number 2. And we're going to look at these points 3 and 4. So last time we said that if this is constant, I tend to write it as pressure divided by unit weight plus elevation. I just switch these terms around, plus v squared over 2g equals constant. And you recall that we could write it upstream and then downstream. They have to equal each other. And so what we need to do is we're going to have 6 quantities. Hopefully we only have 1 that we want to determine, and therefore we know the other 5, and we solve for the other one. And that's exactly what we did with the examples we attempted to do. And so that was fine, and we'll do some examples as we go through this. We have another week of talking about Bernoulli, but we'll also introduce a second way of thinking about Bernoulli today, and that is the idea that we can look at behavior as we go across a streamline. So we can go from this point to this point. what will, for instance, the pressure distribution be like as we go across it? So if we're in a swimming pool, I guess we'd kind of expect that relative to the pressure at P4, we might expect that the pressure as we go across it might be equal to P is proportional to the unit weight of the fluid multiplied by the depth at which we go down, right? But it's not a static fluid. It's doing something else. It's not even a horizontally translating fluid. And so the question is, what is this distribution as we go across here, if we want to be able to do that calculation? And so we can use Bernoulli to talk about that term. And so one way to look at it is to go back to our expression for Bernoulli. I made the case before that this is just an exposition of Newton's second law. Forces in one direction, actually forces in three directions, right-hand law, is equal to mass times acceleration. And so, and we also, when we talked about this, it won't come as a surprise that this expression is equal to, forces are equal to angular acceleration. And we talked a little bit about this, about the idea that we could take a weight which has a mass attached to it. Oh, so actually it'll be a weight which is equal to a mass times gravity. And we can look at the force that is a tide attached to that as a result of swinging this at some kind of velocity v theta. And of course this velocity is in a curve, right? Because I'm swinging it around my head, or actually in this case I'm swinging it in a vertical plane. And so what we can look at is the fact that force is equal to mass times acceleration. We can write this acceleration as the velocity squared divided by the lever arm. And so this lever arm is of some radius. And so if we want to think about our particular example, let's see how this works. See if it's going to make us, oh, isn't that amazing? Technology these days. This is our Jaguar. Stop. I was saying technology is amazing. But not so amazing sometimes. So this radius is here. And so this is the force that's pushing it upwards. This is the force that's trying to pull it down. And so if we wanted to, we could equate the fact that mass times gravity is equal to Fr, which equals mass times v theta squared over r. In each case, if we wanted to, we could also, well, we could get rid of the masses. We could also divide it through by a volume. And the reason for doing that is that this now is a density. You can think of this as a density. Doesn't really matter because they both cancel out. And so we could write this as G is equal to V theta squared over R. And V theta, by the way, I always get this, theta is equal to the radius times the angular velocity, numbers of revs per revolution. So we could convert this into revolutions per second if we wanted to. But this says, this is, I've written it as an equality, but I suppose we could think of it that this has to be the case for it not to fall down, right? So gravity, when I'm upside down in the car, is pulling down on me. so long as gravity not to be larger than the force that's acting up on me by my centripetal motion, this term has to be larger. So this equality can be thought of as a requirement for us to be able to determine exactly the velocity we need to go at. So if we write it as an equality, why can't I do this? Okay. And if we write it this, so we have to be going at a velocity which is equal to gravity times r square root, right? Just by rearranging this. Or the minimum radius for a given velocity that we have has to be equal to v theta squared over g. We're always doing it on this planet, but if we're doing it on a different planet, I guess the radius could be, if it was smaller, then the radius would have to be larger. Or if we were doing it on the moon, the velocity would have to be faster to do it. And so this is the actual velocity we have to be going at, the minimum velocity, such as we don't end up on our roof on the floor here, basically. And so that is exactly what we're talking about today. And in previous years, I would kind of derive this expression. I'm not sure that that serves us much purpose. Let's just take it as a standard result. If you really want to look at the derivation of that, you can look at last year, and I derive it from the rotational equations that we used, that we did when we looked at a container that is twisted on its central axis at some velocity, and it gets this arcuate surface to it. We just use this expression. It's really just a reuse of this expression f equals ma, and we come up with a standard result. But instead of that, let's use this expression. You can see what the individual components are: pressure head, elevation head, and velocity head, inertial term. This is the mass times acceleration term. And what we can do is, just as we did with Bernoulli last time, is we can write it at two particular points, but those points will be points going across a streamline. And we also just need to be able to remember that this is the streamline velocity, right? If you're looking at the velocity along a streamline, which is in this direction here, the definition of a streamline is that perpendicular to that streamline, the velocity is zero, right? If you align a coordinate system in the direction your car is going, that's the maximum velocity. The velocity of your car in the vertical direction is zero. And so that's the same here. So this velocity that we're using is the streamline velocity, not the normal to the streamline velocity, because the term would be zero. And so I'm going to go through an example that's in the book. We don't need to go through the derivation, blah-de-blah-de-blah. Is this. And it's a relatively straightforward situation. So we have water flowing over a bump. It's the same as a car going down a road. You could think about it as a car going down the road. As you drive your car, I'm just drawing a cartoon. I'm not going to use the cartoon. But if you're going down the road and you go down a bump and you go to the bottom of the bump and get pushed up, you feel that you're sitting more heavily in your seat. If you do the converse and you go across a bump which is elevated, then you are flying off the top, and it's like going up, well, actually it's not a good analogy. Then you feel that you're weightless if the bump is high enough, right? You can get airborne as you come up across this. And so those different weights that you feel of yourself should be some clue as to what the pressure distribution might be as you're going across a valley that you go into the bottom and you accelerate back up out of. You might think that the pressure distribution is larger than it would be at just gravity, and this might be less than just at gravity. And so those are the basic ideas of what we'll talk about. And so we'll see if that's the case. Success. So I'm going to use a more reasonable color. So let's look at this here. Let's write the equation down that we had, which is P plus gamma z plus integral v squared over r dn equals constant. That's this expression that we had. I'm just quoting it verbatim. So I'm going to remove constant in a minute when I do my other things, but for now let's put that. So we're going to talk about these 2 points here. So let's look about going at points 1 and 2, and let's write out this equation for exactly that. So we could write this equation as equal to, can I squeeze it in? We are going to think of this as going around a radius. So clearly this is a radius. So for this particular case, we're going at some velocity, which we'll call v theta. And that would be the velocities at each of these points, which would be v2 and v1. There'd also be a pressure, P2, on the top. Free surface, so it's equal to 0. P1 on the bottom, don't know. That's what we'd like to know. And we also know that for these, if we draw a line to the center of the radius, this particular radius is infinity, right? The radius of a straight line, r, between the center of rotation and this is infinity, right? It's a horizontal arc. So radius in this particular case essentially goes to infinity. And so with that, what we can do is we can define our coordinate systems. This, if we look at the magnitude of the other important thing to have is that we have a direction here which we're going to call the normal direction. And it's a normal direction to the streamline, and it points in towards the center of rotation, which is an infinite distance away. We could have drawn infinitely upwards as well, I suppose, but we'll use it downwards here. And so this is this, and of course this direction here will be the r direction. And so you could think about this, a small distance in the r direction is equal to a minus distance in the n direction, just from the orientation of these. One is in this direction, one is in this direction. An increment in r has to be equal to a negative increment in the n direction. And so that's what we're going to use. We're going to write this in terms of our terms. P1, Z1, V1, P2, Z2, well, I say 2, but I write 1. We're going to take, just for convenience, V1 equals V2 equals V phi theta. Roughly correct. In this case, it's exactly correct, I think, just from the geometry. In this case, it'll be roughly correct. And then we're going to solve for what we don't know. So what we don't know, I suppose, is P1 is equal to P2 is equal to the unit weight of Z1, minus unit weight of Z2, Z1, I can't speak this morning, and it's going to be equal to the integral V, actually I'm going to write just as V, squared over R dn plus the integral V squared over R dn. But these will have different limits. So this one is for the first one. It's going to be, minus. This one here is this one. This one here is this one. And so these are going to be different limits. So when you integrate something, we're going to integrate from the center of this point r equals 0 to r1. And of course this one here will be r2. And so these integrals will be what? This one will be, we took it from here, so this is the second one. Second one is between r equals 0 and r2. The first one is between r equals 0 and r1. And you know, I'll draw it somewhere else. I know you're copying this down. This looks like kind of a blunt implement, right? If we integrate a function f of r, whatever that looks like, then if we integrate it between r equals 0 to r equals 1 to r equals 2, then this term here is going to be equal to, if I change my color, I'm going to get rid of my color. So this integral here is basically the area under there. This integral here is basically the area here. And you're too compliant. You're not stopping me, right? This should be.
Another question. In the original
Yep.
equation that we had used density. There's like density times the integration of v squared over r dn.
Density was ahead of it.
Yeah,
Okay,
so.
that has to go then. Yeah. I have it written here. You're right. You're exactly right. Density is ahead of it. Right. Gotcha. Thank you. So density can be in or out. Thank you. And so if we subtract these integrals for each other, I guess all I'm doing is I'm trying to get to a place where I can write this expression as P1, I'm not doing a very good job, is equal to P2 plus unit weight Z2 minus Z1 plus density, and I could write those two integrals as the integral R2 R1 minus, because of the way these are, and it's V squared over R dn. So in this particular case, we want to take this term here, and we know that dr is equal to minus dn. So we could just replace this with minus dr. So this will go back to being positive. And the other final deflating thing that we realize is that r is infinity. So anything divided by infinity is going to be equal to 0. And so this whole term here disappears and is equal to 0, irrespective of whether you have density or not. So this term equals 0. And so the bottom line is that our expression that we want is exactly this. And this is exactly our swimming pool equation. And so this says that Z2 is larger than z1 because our positive z direction has to be upwards. Right? This direction has to be upwards in our system. And so all this is saying is that the distribution of pressures that we have conform to dp dz equals minus gamma, our static expression. So it's saying that the pressure at point 1, which we're calculating here, is just as if we were in a swimming pool. All the fluid is moving along at whatever speed we want, 0 or 100 meters a second. But regardless, the pressure at this point varies just as if it was a static fluid. So that's the easier one of our systems. Okay? So now what we'll do is we'll do it for this one. I'm going to clean off the stuff I have on the right-hand side. We'll have the same things defined here. This is going to be dr equals dz. This is going to be the direction dn. This is going to be our streamline velocity, which will take as v theta, which is the same as 0.4 and 3. And the only other thing that we need to get, I realize this is getting to be a crowded diagram, is to look at these two radii. So this is radius 3, and this is radius 4. And I'm going to cut my losses and make this, get rid of this. And attempt it again. So I'll try and write the equation out correctly this time. So we are interested in finding out the pressure at point 3. So the pressure at 3 plus the unit weight times the elevation of 3 plus the integral density v squared over uppercase R dn is equal to the pressure at 4, which is 0 pressure, atmospheric, plus unit weight elevation of 4 plus the integral v squared over R with the density in there dn. We want to determine behavior in terms of P3, so let's separate everything to the right side of that. So the other terms will be the same as before. It will be P4, which we know, which is going to be equal to 0. Atmospheric, it's on the surface. The elevations are going to be equal to the unit weight times Z4, this term here, minus this one here, and it's going to be plus the integral density v squared over R dn. Because this integral is between R4 and R0, and this one is between R3 and R0, then when we subtract this integral from this one, it actually turns out to be, I think it was wrong in the previous case, it didn't matter. It should be R4 and R3. And so, you know, the picture then, if we have it, is this function R4, R3, R0. This is a function of n, actually, I guess, rather than R. If this is this, then the upper limit integral is this amount here, right? The integral below this term here and this term is all of this shaded area. The integral up to R3 is this shaded area, this term here. And so subtracting those from each other, subtracting this whole area from this area actually gives us this area here, right? This is what this represents. And all we need to do is be able to figure out exactly our final manipulation. So the pressure at point 3 is equal to 0 plus the unit weight of the fluid Z4 minus Z3. So this is what we call would call our swimming pool distribution as we go from one point to another, plus a term which is equal to density. I'm getting crowded. What am I going to do? I'm going to move down a bit, which is equal to density V squared over R dN integral between these 2 points. And I suppose we could write this, if we wanted to, the integral density velocity over R squared dN. If velocity is a constant, radius is roughly a constant. If we just take the radius as equal to R and use the same one for both of these, then we can take this to being density V squared over R integral dN between R3 and R4, which is the same as the density V squared over R. What is this integral? It's just the distance between these points multiplied by, it's just this length. So it's just equal to R4 minus R3. In other words, it's the difference in the z's that we have here. And so the final manipulation we need to note, kind of a long derivation, is that this dN is equal to minus dr, because they're in different directions. N points towards the center of gravity, center of rotation. R points outwardly. And so all that does is it turns this positive into a negative. And so, not putting any numbers into this, but understanding what it is, it says that the pressure at this bottom of this distribution is equal to our swimming pool effect, just the static fluid varying with depth z is vertically downwards, so this is the vertical direction, so it just goes up with this, minus a pressure which has to be a positive value. Density is positive, velocity is a positive velocity, it's not directional, it's a speed, and radius is positive, and so this is a positive component, and the difference between radius 4, which is larger than radius 3, is positive as well. And so multiplied by this negative sign, it means that if you look at points R3 and R4, then the pressure distribution, instead of being the hydrostat, which is this, it's going to be less of it than some amount. And the amount less would be equal to, is equal to this. It's going to be less by this amount here. So in other words, this distance here, if this is pressure, this distance here is going to be rho v squared over r, R4 minus R3, which is actually the same as Z4 minus Z3. Z is higher than this, and so it's a positive value. And so this would be the hydrostat, just a swimming pool. And so the pressure that we'd feel as we get lifted off our seat, as we go across the bump, is exactly what we might expect. And that is, if we go fast enough, we can be weightless, right? We can absolutely be weightless as we go across this bump. The opposite would be the case where our radius of curvature is acting downwards. So the radius, center of radius of rotation is above us, and then we go into the dip, and the analysis would be exactly the same. All we'd have to worry about now is that these would be different from each other, and the direction of z would be different. So that's it. So I know that might, perhaps the first pass through this wasn't so obvious, but it's worked out here in exactly the same form, and perhaps is quite apparent. It's Bernoulli, pressure heads, elevation heads, velocity heads for this. I guess this, no, this is the one where they're parallel to each other, so we've already thrown away the velocity head term. And because we throw it away because we're going at the same velocity at each of these points, so it cancels out. And the one that's interesting is the one where we go over the hump. So again, this is Bernoulli. So the pressure at point 4 plus elevation at point 4 plus the velocity head at point 4, which is this term here, and the pressure at point 3, the elevation at point 3, and the velocity term, which is this part here of this integral. And if you go through each of these, the pressure at point 4 is equal to 0, so it drops out. And so we're just left with this term here. The unit weight term is the difference in elevations between these 2 points, which we had, which is just taken as the height here. And we have this extra term where density is positive, velocity is a speed, which is always positive, and rotational radius is always positive. And so this term has to be positive, and it's subtracted from this distribution, and therefore the pressure at this depth must be less than if it was just this term alone, right? That's it. And so hopefully that makes kind of sense in terms of what we're doing. And so that's exactly, and it's explained, so if you want to go through it and torture yourself some more, then you can look through the rest of this material. Questions? Not straightforward, but manageable, yeah.
For the graph you drew for R4 and R3.
Say it again, for the what about R3 and R4?
Yeah.
For the what?
Keep going up a little bit. That one, the blue one to the left, is the, I guess the x-axis, is that pressure?
Yes, sorry, yeah. Yeah. P for pressure.
When we go over the hump there, for points 4 and 3, we just assume that it's a singular velocity moving through there, even though it would be like faster at the top and slower at the bottom?
Yeah. You could have them as different velocities. It gets very complicated because this term on the integrals become 2 separate velocities, 2 separate radii. And so the concept is, the effect is what you'd expect. And of course, you know, to go up on this, there's also a radius of curvature here, right? So there's a portion of this is this part. And so I think, you know, as you go up into this, you'd be pushed back into your seat. If you imagine yourself driving on a road, then you're going on a different radius of curvature. Yeah, you know what you'd feel. You'd be pushed into your seat before you go airborne, and then I guess you get pushed into your seat again when you crash on the ground, and keep on going. But it should all make sense. And so if you're going fast enough, or the curvature is right, you can potentially get this distribution to move all the way here. And airborne means that the restraining force pulling you down is exactly the the restraining force that you need to pull you down is exactly the same as mass times gravity that's resisting you going up. So that's it. Usually in this class, I go through a couple of examples. You know, we looked in the videos early on as an example that looks at a loon flying into water and air and going between the two. This is air, this is water, and it asks you what velocity in water do you have to be going at for the pressure on the beak of the loon to be the same. And so that's taking account of the fact that as it goes across the water at point air to point W, you can write Bernoulli's expression as pressure W plus VW squared over 2g. Elevations are the same, so let's not worry about that, is equal to the pressure in air plus velocity in air squared over 2g. The fact is that this point A and point W is where the loon's beak is as it goes from one to the other. They're essentially at the same elevation. And the question is, what is the same to produce the same dynamic pressure? And so that means when is PW equal to P air? And so you could write, each of these expressions in terms of each other. So I suppose we could well, it's just going to be when VW squared over 2g, this is unit weight, of air. So it would be gamma W BW plus gamma air V air squared over 2g. So this is equals. And then if you know the air speed is 40 miles an hour, you know what this is, you know what gravity is, you know what rho g air is, you know what rho g water is, and so the only term is to solve for VW squared. And I only mention that now at the end because I noted last night that my solution was wrong last year. So don't get your solution from last year's video. It's all, you know. So you can write Bernoulli at each point. So the bottom line is that you can solve in terms of P air over P water has to equal 1. And so you can just look at the ratio of each of these. So that's exactly what this expression is here. So, and we didn't get to it, but I think the solution from last year for this is right. This is Jesse Sharp going across the top of the falls. How do you solve this? The question is, if you know that you're going at the speed of the Niagara River, so you know that point 1 is V1, which you know the atmospheric pressure is defined, and you know that the elevation is equal to h. You know everything about Bernoulli at this point. You can do two things. You can calculate the velocity that you're going at just before impact at point 2, or you can calculate what the pressure is you develop as Jesse Sharp hits the water at 0 velocity at point 3. And so if for each of these points we realize that at point 2 we don't know the pressure, oh sorry, we do, sorry. Pressure is still atmospheric because we're in the air. At this point, the velocity 2 we don't know, but we do know that Z2 is equal to 0. This is just the datum that we've taken, just above 0. So if you write Bernoulli for points 1 and point 2, you end up with 6 expressions. There's only one of the things you don't know. You don't know what V2 is. And you can solve for his pre-impact velocity, just he's about to hit the water. And at point 3, we know that at point 3, we don't know the pressure because it's like the air hitting the side of the truck. We know it's stagnated as it hits the truck. It's going at 0 velocity. We do know that V3 is equal to 0. We do know that the elevation C3, which is essentially equal to this, right? They're the same as each other, is equal to 0. And so the only term when we write Bernoulli between point 1, which is here, and point 3, which is here, the only term we don't know is P3. And it solves for each of these, straightforward. So that's kind of Bernoulli in a nutshell. So we covered both of the things we need to now. I guess next time we do some examples. We've got another week messing around with Bernoulli, but those are the basic principles for linear acceleration and also for rotation. Great.